This video is focused on kinematics or summary of kinematics. You should have already watched a video on the kinesiology model. In that model, I go through how all the different elements of a department of kinesiology and nutrition sciences sort of work together to understand human performance or how well we do something. And as I talk about in that model and in the structure summary presentation, a performance is nothing more than a bunch of movements put together. And we're dealing with human performance here. So it's movements like flexions, extensions, rotations, abductions, adductions, etc. Those movements all have specific names, and we learn those names in a course like anatomical kinesiology. And we also need to understand the structure of the human. We need to understand bones, we need to understand muscles, how muscles contract, and so forth. So all of this is sort of in your anatomy and physiology courses, as well as your anatomical kinesiology course. And I've got a separate video summarizing that. But continuing with this model, from a physics perspective, movement is simply defined as some change in space over some time period. And so I'm going to put the term displacement here just to get used to using a term that we'll use in our biomechanics. And I'll put the word time. So movement is a change in space in some time period. Now, sometimes we're interested in things that are not moving, and that would just be no displacement. And from your undergrad biomechanics class, you should know that displacement is just simply the straight line distance between 2 points, an initial position and a final position. And it's a vector, and it's represented by magnitude and direction. And so in this presentation, I simply want to really summarize and review just briefly kinematics, the study of motion without concerning the forces causing the motion. That's going to be the next branch of mechanics, which would be kinetics. So kinematics is the study of motion. And in undergrad biomechanics, you would have spent a lot of time on understanding position, velocity, and acceleration relationships. And by position, I really mean change in position, but we often refer to these as PVA. A PVA model, position, velocity, and acceleration. And when I teach undergrad biomechanics, I do a lot of graphing of these three positions because there are three parameters. They're all related mathematically. And in kinematics, we look at two branches of kinematics, and that is linear and angular. Linear is straight line. All points of an object travel the same distance, and distance is the very similar term to displacement, but distance is a scalar, and it represents the total change in length. So we have total change in position of all points of an object travel the same distance. That's linear motion, and angular motion is motion around an axis. And we have different types of linear motion. We have curvilinear, we have rectilinear, and then we have angular motion, which is motion around an axis. All right, so in the linear world, you should be familiar with terms like distance, as I just mentioned, total change in position of an object. You should know the units or any units of length, meters, yards, miles, kilometers, what have you. And then displacement, which is the straight line distance between 2 points. And we use the formula delta S equals SF minus SI. This is a vector. It's represented by magnitude and direction. So remember that I'll put this down here. Vectors are represented by magnitude and direction. And the importance of this is when we do our math, we have to really be careful with not only understanding the magnitude of the parameter, but also the direction that the parameter is headed in. So just know that when we identify a parameter as a vector, we need to account in our math computations that are accounting for both magnitude and direction. So displacement is the final position minus the initial position. It's represented or by units of any units of length, yards, meters, kilometers, what have you. And in essence, these two are closely associated with each other. If I'm in a physics class, I would often say the displacement is the magnitude of the displacement vector. And that works well when our delta t of our analysis is really small. But often in biomechanics, we distinguish between these two parameters because sometimes we want to look at the total change in position, maybe running a marathon from point to point, that's a 26.2-mile length, that's a distance. But the point to point, if you just do final position minus initial position, may not be 26.2 because the delta t is, 2 hours, 3 hours, what have you. So often we distinguish between these two parameters in our world. So that's a linear position, and then the next parameter is linear velocity, and that is time rate of change of displacement. And we use the formula V equals displacement delta S over delta T. I don't have an equation for distance because I actually just pull out my yardstick or my meter stick or some type of tape measure to measure that total change in length. So I'm just going to go forward with velocity as being change in displacement over change in time. Final position minus initial position over final time minus initial time. Units are any units of length over any units of time. The term that's, and this is a vector, that, sorry, I'm messing up. Okay. The term that's closely associated with velocity is speed, and speed is a scalar. It's represented by magnitude only, and it's simply the distance over time. So we have two terms that are scalars, distance and speed, and two that are vectors, displacement and velocity. And it's good to be able to distinguish how they're similar and where they're different. And again, if I'm in physics and my delta t of analysis is really small, I may say the speed is the magnitude of the velocity vector. The third parameter that we deal with is acceleration, and acceleration is the time rate of change of velocity. And we use the formula A equals delta V over delta T. This is a vector, has magnitude and direction, and in biomechanics, undergrad biomechanics, we spend a lot of time trying to understand this parameter and the importance of it, because ultimately it will link us to kinetics using the formula F equals ma. But acceleration, what's important to understand is this is telling us how fast velocity is changing. And the direction of the acceleration vector does not tell us the direction of motion. I always use the example of a projectile. Projectile is any object that's flying through the air with really the force of gravity being the only force acting on the object. It's going to undergo an acceleration of negative 9.8 meters per second squared. I'm sure you've heard that number before. That's simply telling us how fast velocity is changing. We don't know simply that saying a projectile has an acceleration of negative 9.8 meters per second squared. We don't know if that object is moving upwards and slowing down at that rate, or if it's moving downwards and speeding up with that rate. Same acceleration, negative 9.8 meters per second squared. So the direction of the acceleration vector does not tell us the direction of motion. All right, and units for acceleration are any units of velocity over any units of time. Meters per second, which ultimately translate to meters per second squared. Miles per hour per second, any units of velocity over any units of time. All right, so those are our three parameters, actually 5 parameters under linear kinematics. The other world is angular kinematics. And in the angular world, what we actually learn and spend quite a bit of time on is first understanding the different types of ways to describe angular position. And the two types of ways that we use to describe angular position are absolute angle and relative angle. Absolute angle is also the same as saying segment angle, sorry, I can spell. Relative angles are the same as joint angles. An absolute angle is the angle between a body segment, thigh, leg, arm, forearm, trunk segments, and some fixed line in space. A right horizontal, a vertical line, upward vertical line. And what we're doing is we're describing where a segment is relative to a fixed reference line. That reference line won't move. And so we're able to describe the position of a segment in some reference frame. A relative angle is any angle that is between two anatomical segments, with both anatomical segments having the ability to move. So that's what we also call these joint angles, like an elbow, a knee, a hip. Those are the angles between, the elbow is the angle between the forearm and the upper arm. The knee is the angle between the thigh and the leg, both anatomical segments. These two are ways of representing angular position are very important, and we use both of these quite a bit in biomechanical analyses. And so you want to be familiar with both of these ways to represent angular position. Okay, so now that once we have the angular position, the terms for angular kinematics are going to be, in terms of position, velocity, and acceleration, are going to be very similar to linear, but just different, different symbols. So angular, I'll do a line here, angular displacement, we use the symbol theta, and we'll do angular displacement is the final minus initial angular position. Okay, so that's our equation for angular displacement. It's a vector, and it's represented by magnitude and direction, and we need to account for that direction. In this case, our direction would be something where we define counterclockwise as motion as being positive. Over here, we would typically say up is positive or forward is positive. So this is just a way to define ultimately our reference frame. Okay, angular displacement. We also have angular distance, which is the total change in angular position. So if we do multiple revolutions, a 2.5 somersault, that 2.5 is actually representing, or is represented as angular distance. Angular displacement is simply the final position minus the initial position. 2.5 somersault would actually lead to an angular displacement of 1/2 of a somersault. So that's awkward, I know, but this is why often we try to define, we pick which parameter is useful for the time window that we're looking at. If we're looking at very small delta t's, we typically are working with angular displacement. If we're dealing with a movement that has multiple revolutions, we would select angular distance. Both have the same set of units, radians, degrees, or revolutions, or somersaults. But displacement is the vector and distance is the scalar. The next parameter is angular velocity. And in this equation, we use the term omega, and we calculate the time rate of change of angular displacement. So delta theta over delta t. Units for angular velocity are units of angular displacement, so degrees per second over units of time, degrees per second, radians per minute, whatever it is. This is a vector. It's represented by magnitude and direction, and again, the direction would be indicating which way the object's rotating. We also have angular speed, just like linear speed, and that is simply angular distance over change in time. This is a scalar, this is a vector. Velocity is a vector, speed is a scalar. All right, so that's our second kinematic parameter, angular kinematic parameter. And then the final one is angular acceleration. or acceleration. And in angular acceleration, we use the symbol alpha, and that is equal to the time rate of change of angular velocity. So delta omega over delta t. It's represented by units of angular velocity over units of time. So degrees per second, which translates to degrees per second squared. Radians per second per minute, any units of angular velocity over any units of time. This is a vector, and I do not do any parameter for rate of change of speed for either linear or angular world. I just stick with the vector, angular acceleration and linear acceleration. Okay, so that is part of our model. We're at displacement and time, and in displacement and time, we are in the branch of mechanics of kinematics, the study of motion. We have linear kinematics and angular kinematics we need to understand. Oh, and by the way, the combination of these two, when we have movements, general, oh boy, boy, I'm not spelling very well this morning. Sorry, general. All right, there we go. Yeah, yeah, I could cut this out of the video, but I'll leave it. We all make mistakes as we go along. Um, Kinematics, we have linear and angular types of motion. The combination of those two kinds of motion, which is most of our human movement, is simply a general motion. But when we have a general movement, we actually go back and do a linear analysis of a movement, and then we'll do an angular analysis or vice versa. And then we put those understandings of those analyses into understanding general movement. We're really understanding the relationship between position, change in position, velocity, and acceleration. We have linear parameters and we have angular parameters. And as you go through this course, you should be familiar with all these terms as well as reference frames. And then we'll be applying and using these terms throughout the semester. Okay, I hope that's a helpful summary to kinematics. Thank you.